We are going to make a graph of potential energy versus the progress of a reaction. The reaction we will look at is the bromination of an alkene. This is a reaction mechanism you guys will have to know for chapter 4. So let's get a good understanding of it right now. First thing is to remember what the orbitals look like in an alkene around the double bond. The first bond is a sigma bond, and it is a result of the overlap of these sp2 hybridized orbitals. And then the second bond is the result of the overlap of these purely p orbitals. And what it looks like when they overlap is electron density in places above and below the carbon-carbon bond. So the electrons hang out away from these carbons. So there's just electrons like sticking out away from the middle of the molecule. So these electrons are just hanging out there, and they are free to interact with anything else. So anything that's positively charged will be attracted to these electrons, or these electrons will be attracted to anything that's positively charged. What we call that is a nucleophile. In this reaction, the bromine, or one bromine atom in the bromine molecule, is able to act as an electrophile. So these electrons that are hanging out below or above the carbon-carbon double bond are attracted to the bromine and form a bond with the bromine, and then the electron pair that the bromine shares goes to the other bromine. As a result, the two electrons in the pi bond that were being shared between the two carbons are now no longer shared between the two carbons. They're now shared between a carbon or the two carbons and a bromine. And the result of that is the bromonium ion, which looks like this. But this is not the best way to write a bromonium ion, because really there are multiple resonance structures that contribute to the structure of this ion. Here is, what we're looking at is just one of them. Here is another one. If the electrons from this bond were to go to the bromine, we would find a contributing resonance structure like this, where the positive charge, instead of being on the bromine, is on a carbon. This is a little positive charge here. And similarly, there's another resonance structure where the other carbon has the positive charge. So what the actual bromonium ion looks like is a combination of all three of these resonance structures. Because there are resonance structures where the bromine is not bonded to one of the carbons, the bromine-carbon bonds are not full single bonds. We have to consider them as having a bond order of less than 1. So these bonds are going to be a bit longer than normal single bonds. Remember that, that's important for the next part. Finally, the last thing that happens is the bromine that got kicked off a while ago comes back, and he is attracted to one of the positive carbons, and we have this movement of electrons, and we have formation of the final product. And I'd like you to notice that in the final product, the bromine that went on first is now single bonded to the carbon, so the bond length is shorter. When we look at the energy profile of this reaction, the potential energy of the species involved versus the reaction progress, we can use the length of this bond between the carbon and the first bromine that goes on as our x-axis. Usually the x-axis on an energy profile of a reaction is just vaguely described as reaction progress or reaction coordinate, which can be kind of complicated, but just for funsies, we can graph specifically the length of this one carbon-bromine bond. The energy profile starts with the reactants before they start to react. So here the bromine is separate from the ethene, and the bond length is long. By the way, going to the right here means a shorter bond. Then we know from the mechanism that we're going to have a bromonium ion intermediate formed, which is a species where the bond length is greater than that of a single bond, but less than when the bromine's just floating around separately. And what makes an intermediate is it's not the product of the final reaction. It may be very short-lived for less than a second, but it is at the bottom of the energy profile. What that means is that going to the left the energy goes up, going to the right the energy goes up from an intermediate. So the other species we're interested in is the transition state species, which is somewhere between the bromonium ion intermediate and the reactant. And the transition state is the geometry at which the energy is a maximum. So when talking about the carbon-bromine bond length, it would be longer than in the bromonium ion, but closer than if the bromine is just floating around next to the ethene. They kind of get crammed together, and that's unstable. But then the reaction happens, and the energy decreases as the bromonium ion is formed. But now, moving on from the intermediate, we head toward a second transition state, where the second bromine kind of bumps into the back of this bromonium ion. So we get a transition state at an energy maximum here. And then as that second bromide actually forms a bond with one of the carbons, the energy decreases, and the bond length of a first carbon-bromine bond gets shorter as it becomes a full single bond, and you have product formation, which is at the bottom of the energy profile. So that's another important thing to note, is that reactants and products are at the bottom, transition states are at the top, intermediates are at the bottom. One of your assignments for Chapter 3 is to make an energy profile like this, based on energies you calculate for a twisting reaction. So when you do this, what's going to be on the x-axis is actually an angle. So I hope you enjoy that activity.
Made with Doodlecast Pro.